All right. So in 13.1, we introduced the idea of a formal language and looked at one particular way of defining a formal language with a phrase structure grammar. We're going to kind of set phrase structure grammars aside for the moment and look at some other things. Just focusing on the idea of a formal language itself. You've got some sort of subset of some set of strings over a vocabulary, right? And let's take C++ just as our example. If you type in a sequence of characters, right, then it could be correct in C++, meaning it's like follows the syntax rules, and it is actually a valid string in the C++ language, or you could have made a syntax error and maybe the string is not actually in the language. You need some way to check that. And in fact, that's one of the jobs of a compiler, is to look at what you typed, right, to scan through it and check to make sure that the syntax is correct, meaning essentially, is this massive string that you typed in, right, because like a single program file is just a long string, all right, of characters. The question is that string in the language, right? That's one of the things a compiler does, and it finds errors if there are any. It would identify where there's a syntax error. So what we want to do is introduce the sort of an abstract theoretical machine that can do that. It can check to see if a given input string is in a certain formal language. To do that, we are going to look at a type of thing called a finite state machine without output, which is also known as a finite state automaton. We're skipping a section here where the textbook introduces finite state machines with output, but we don't really need those ones. Okay, so there's a little bit of background that's introduced in that section, but we can kind of make up for it here. Basically, we are talking about a theoretical machine, and so what it is gonna be is just sort of a mathematical object that has a bunch of different states that it can be in. And then it's going to have it's going to take some sort of input in the form of a string over an alphabet, and then it's going to have something that tells the machine how to transition from one state to another state when it receives inputs. And then at the end, it is going to give some kind of basically a yes or no sort of output. This is called a finite state machine without output, but really there is one output at the end, which is it's basically like a yes or no. The type of machine that does have outputs is giving you a bunch of, like, a whole string of outputs as you go. But this just gives you a single yes or no answer at the end, which is what we want. Because so, like I said, I'm gonna define this, and then I'm gonna do an example. But I want you to think of this like from the perspective of this is a machine that is essentially taking an input string and checking to see if that input string is in some specified language. So we're going to build the machine for the language that we want. All right, so the machine itself is called M, and just like a grammar, it is a tuple. It is, in this case, a 5-tuple. So it has 5 distinct parts: SI, F, S0, and capital F. Where the S is the set of states. So I'm going to write that out. And the elements, the states are usually just written as lowercase s with subscripts, starting with S0, which will be specified in a moment, S1, ... all the way through to Sn. Now, the fact that this is called a finite state machine means that there needs to be a finite number of different states. And these states could have different names, but just for the sake of kind of simplicity and uniformity, we're just going to always refer to them by, S0 through Sn. And what order they come in doesn't particularly matter, as long as they're just distinct from each other. Okay. So this would be some finite set of states. And you might ask, like, well, how many states are you going to need? Well, that depends on the language you're trying to check, and it also depends on like how you are designing the machine. So we'll determine how many states we need as we go when we build the machine itself. So then we've got I. I is your input alphabet. it is the set of characters that the machine is expecting as inputs. So like in C++, that set is huge, right? It's like any character you can type into a computer. But in our cases, we're going to keep it limited to things like ones and zeros. In many cases, it's just going to be 0 and 1. Then we have f, this function f. Well, yes, it is a function. You might have guessed it by the fact that it's called f. But it is a function. It's called a transition function, and its domain is actually a Cartesian product. Its domain, it kind of has two inputs. Its input would be like an ordered pair. A state, so an element of S, and an input character, which would be an element of I. So basically what the transition function, I'll put that down here. What the transition function does is it is the thing that tells the machine when you are in this state and when you receive this input, transition to this other state. So the outputs of this function are elements of S. So it's a function from S cross I to S. This is like a two variable input function like you have in Calc 2 or Calc 3, for example. And basically the sort of fundamental structure of the machine all comes in that transition function f. That's where all the juicy good stuff happens. The last two parts here are still important. S0 is just the designated starting state. So we are always going to assume that when the machine begins to receive its input string, it starts in state 0, S0. If this was a real-life machine, like an actual machine where there's sort of a mechanical one or like a digital machine, it might need to be reset every time it receives, it's getting ready to receive an input. But you can imagine that happening sort of automatically. And it's an element of S, of course. It's S0 right there. And then the last part of the machine is F, and capital F is a subset of S, and that is the set of what we'll call final states, which are also called, another term for that is accepting states. And that, if we want our finite state automaton to essentially answer a yes or no question, like, is this input string in the language this machine is designed to recognize? The final states are what allow us to do that. Essentially, we're going to give it an input string, and it's going to transition. It's going to hop around between states, and then when the input string ends, we look at the state the machine is in, and if that state is in the set F, meaning if it is an accepting state, then the machine accepts the input string and says yes. That input string was in the language. Otherwise, if the machine ends in a state which is not in this set of final states, then the machine would say no, that input string was not in the language. So F is important in order to answer those yes or no questions. Okay, so that is the definition of a machine. Now let's look at an example. So for this example, I'm going to have two states, just S0 and S1. And I'm going to use the input alphabet 0 and 1. So we're talking about binary inputs or bit string inputs. And then the final state is just going to be S0. We'll get to that in a moment. Okay, so an automaton or any finite state machine can be represented in a number of different ways. The main two would be as a state table or state diagram. So this on the left is going to be a state table. Actually, oh yeah, sure, yeah, I'll do it left and right. And then we're going to draw a state diagram over here in a moment. And the state table and the state diagram essentially are a representation of the transition function and what it does. So I've labeled this F right here because it's the transition function, F. We have a two-dimensional input, right? We've got the set of states, so that's our S right here. So we have S0 and S1 as our two states, and then we also need to have an input from the input alphabet, I. So we have 0 and 1 over here. So those are our 2x2 input, so then we have 4 different possible combinations, and we need to determine what the output is. So I'm going to fill in this grid with what states I want to transition to. Now, I haven't told you what this machine is for or anything. We're going to look at it and then figure out what it's for. Okay, so there's the state table. This is these are the outputs, the output states. Remember, the f function gives us outputs in S. So we have inputs and then we have outputs. So now let's draw the state diagram. For the state diagram, you usually represent each state by a circle, which is essentially, those are the nodes in a graph. Okay, what we're going to do is represent this with a graph. It's going to be a directed graph. And so those nodes represent the different states that the machine can be in. So we have state 0 and state 1. And you designate the starting state with an arrow that points at that, just coming from nothing, but just an arrow that points at that node. So that's kind of similar to how you would designate like the root of a tree, right? Although this is not a tree. So that's our starting state. And then, according to the transition function, we will draw some arrows. And those arrows are going to be labeled by what input they correspond to. So from state 0, if you're in state 0, if you receive a 0 as an input, you're going to transition to state 1. So I'm going to start by drawing an arrow over to state 1, like that. And I'm going to label that arrow with a 0. So that says, when you're in state 0, if you receive a 0 input, you move to state 1. Now when you're in state 0, if you receive a 1 input, you stay in state 0. So I'm going to put a loop over here and label that loop with 1. Now, finite automaton, at least the type of finite automaton that we're starting with, which is a type called a deterministic finite automaton. And there's a type called a non-deterministic, but we're not really going to get into that. I decided to kind of cut that topic for this semester. For the deterministic types that we're going to stick to, every state has to have 2 arrows leaving it. An arrow, if you have binary, if you're dealing with a 0 or 1 input alphabet. So you'd have the arrow leaving for the 0 input and the arrow leaving for the 1 input. So that's sort of making sure that the diagram is complete, right? That it tells you what to do in every possible circumstance, right? Every single one of these grid possibilities is represented in the diagram. So I'm not done here. I gotta now figure out what happens if I'm in state 1. If I receive a 0, I go back to state 0 like this. Whereas if I receive a 1, I stay in state 1. So I'll loop like that. So now that's complete. It tells me what to do in every possible situation, every state and every possible input. Now there's one thing I need to add to this state diagram, which is this information here, that the S0 is a final state or accepting state. And to designate that, you usually get in here and draw a second circle. So we have like a double circle around our accepting states. All right, and if you'd like, in the state diagram, you can sort of circle the state, which is an accepting state like that, to represent the same thing. Okay, so now this is a machine. This is the finite automaton, and it is designed to recognize a particular formal language, which is a set of bit strings. So let's figure out what that is. I'm going to give you several input strings here. All right, so for each of these input strings, I want you to follow through. I'll show you what to do, how to do the first one. If you receive the input 1, 0, 1, first of all, you start in your starting state. I'm going to use the state diagram to determine the answers here because it's the easiest for me to follow through. I like the visual layout. So you start in your starting state, you receive a 1, and you loop. So you're still in state 0. Then you receive a 0, and when you receive that 0, we're going to follow the arrow over to state 1. Now we're in state 1. Move down your string, now we receive a 1, and we loop. And we end in state 1. State 1 is not an accepting state. So does it accept? No. So try that with each of these input strings and see what happens. You can pause the video and give it a shot. Our goal is to figure out, does it accept or not? Yes or no. Does it end in an accepting state or not? So the second one should be a yes. The third would be a no. And the fourth would be a yes again. So I chose these just to kind of help you figure out what this machine does. You may already know what this does. I believe this might actually be an example in the textbook. I can't remember if I stole this one or not. But what does it do? Well, it accepts strings as long as they have an even number of zeros. That's what it turns out this machine is doing. We actually made a phrase structure grammar for this exact language in the previous section, and that phrase structure grammar was super complicated. But the finite automaton that checks to see if a string input string is in that language is very simple, right? It's just kind of jumping back and forth between states whenever you receive a 0, right? If you receive a 0, you jump over to S1, but if you receive a second 0, you jump back to S0 again. And that you jump back and forth, and so if you have an even number of zeros, you would end up back in your accepting state. Now, 1s don't have any effect at all. You just loop, right? So you stay where you are. Essentially, 1s are ignored by this machine. And only the zeros really matter, okay? Because they're the only ones that cause you to change states back and forth. So this machine is checking to see if the input string has an even number of zeros, but we can also think of that as a machine generating the language. So not only is it checking it, it's also, you could sort of flip that around and say it's generating that language. Basically, the language is defined as a set of all strings accepted by this machine, right? And that's equivalent to saying that it's checking to see if a string is in that language. And just like with a grammar, we'll do L of the structure, the language generated by this structure. So we did L of G for grammars. Now we're going to do L of M for machines. In this case, L of M is set of all bit strings with even number of 0 bits.